What is the sound of a zombie screaming? What does that have to do with race conditions? What even is a race condition? Who is this person sitting inside your computer telling you all about race conditions, zombies, and screaming? My name is Josh. I have been developing software with Ruby for about 5 years. I currently work for a company that you may have heard of and almost certainly have used called Braintree. We deal with payment processing, usually credit cards. Before that, I worked at an Internet of Things platform where we tried to connect things to the internet. We had this goal that we would do all sorts of things. We mostly focused on printers. And in my past life and lives, I have used both Ruby and Java fairly extensively. This is also my first time speaking at RubyConf. I've attended many RubyConfs before, and I have always been eager to try speaking at it, and this is exactly how I imagined that it would go. Let's talk about incrementing. This is, you might think, one of the more simple operations that a computer can do, and in a sense it is. But it's not really just one thing. Incrementing is two operations at sort of the computer level. First, you load the value that x has initially, and then you figure out a new value, x plus 1, and then you assign that new value to the variable x, to whatever location in data x is being stored in. The thing that makes that important is the idea of an operation being atomic. So x equals x plus 1 is not atomic because it happens in multiple steps. In fact, most things aren't atomic. Most database operations, most list operations or data structure things, most things are not atomic. So let's look at why that matters. Here we have what's called a sequence diagram. The way we read this is we see those boxes at the top represent things. The lines that fall down from the middle of the box represents kind of that things forward motion in time. So time starts at the top and goes towards the bottom. And then the arrows that flow between them are messages that are being sent or passed between the things. So what we're seeing here is two running processes, each labeled code, and they are running the code x equals x plus 1. They're running the code we saw on the last slide, or 2 slides ago. So the first code comes in. So the way we'll read this is we'll start at the top and let our eyes drift towards the bottom. So we start at the top and we see that x is assigned the value of 0. Then the next thing that happens is the code on the left springs into existence and asks x, hey, what is your value? X replies 0. The code on the left does some sort of extremely complicated math, figures out that 0 plus 1 is in fact 1, and then assigns 1 to x. Then the code on the right comes in and does, well, basically exactly the same thing, except that x starts out with a value of 1, so the code on the right assigns the value 2 to it. Here's why we care so much about this being atomic, or in this case, not being atomic. There's nothing that guarantees that those arrows will get clustered together. So if the sequence of operations had happened in a different order, like so, then we would get the wrong value for x. So what happens on the left is that the code says, hey x, what is your value? Learns that the value is 0 and then assigns 1 to it. The code on the right queries x before the code on the left got around to assigning it. So that means the code on the right tries to update with stale data. This is the secret sauce of a race condition. What that means is we have multiple processes that are interacting with the same shared data. In this case, the two processes are the two codes on the right and the left. The shared data is the 1 byte that is storing the value x. Those multiple processes rely on things happening in a certain order, but then the things don't necessarily happen in that order. When things happen out of order, that is a race condition, that and the associated bugs. So now I'm going to show you just a quick puzzle, which is this. Imagine that we started out with x equals 0 but instead of the codes on the left and the right each incrementing x once, let's say they each increment x 10 times. So the question is, at the end of all this, when we print the value of x, what are the possible outcomes? So now is the moment where I would recommend muting for just a couple seconds, 30 seconds or so, until I move on to the next slide, in case you want to figure this out on your own, because I'm about to tell you the answer. And the answer is a value will get printed. That value will be any number within a certain range. That range has as its maximum 20. That kind of makes sense. There aren't enough increments to cause x to go above 20. The smallest possible value is 2. And so I'll leave it as an exercise to the viewer to figure out what sequence diagram could cause x to wind up as 2 when it gets printed. And now for story time. I'm going to tell you 4 stories, each of which is a moment during my career when I came across a race condition and it caused some kind of bug. It might have been a bug in a test or in some monitoring tools, but in each of these cases, there was a race condition, and I'll tell you how we found the race condition, what kind of impact it had, and what we did to fix it. So story number 1 is called Smurfs Law. Smurf was a tool that we had at Braintree, that we have at Braintree still, that just gathers up data and sends it to one of our banking partners. This is a thing that, in a payment processing company has to happen all the time. So the mechanism by which it does that is various parts of our system will write data to a bucket in S3. Smurf will then read that data from that same bucket, do some processing in order to format the data properly, and then send it off. Of course, we have code running in different environments. So in order to properly separate data, we have one bucket for prod, one for sand, and one for test. The one in prod is appropriately access restricted. The one in sand has sandbox data, and the one in test gets cleared every so often and repopulated during integration test runs with data that the integration tests know about. Let's drill into the tests a little bit. So here's a typical integration test run. The test will start by seeding some data into S3 and then telling Smurf to do its thing and then making an assertion on Smurf that it did the right thing with the data that was seeded. Because one of the things we care about is that Smurf handles changes in data correctly, we do this in 2 steps. So we have a step 1 data and a step 2 data. Here's the bug. We started to see failures. This happened kind of sporadically, but especially once we started actively developing on Smurf. We started to see failures that were associated with we expected the step 2 results, but got the step 1 results. So what happened? Well, imagine that 2 runs of the tests are running at the same time. We have T1 over on the left. Let's say that that's our CI setup running tests against the main branch. And then T2 over on the right, let's say that that's me running the tests on my local machine. And the tests on the left are just wrapping up. The test thing has seeded the step 2 data, and Smurf reads that and then does the right thing. And right after that, my tests start. And so I seed the step 1 data and then etc. Well, again, none of these operations are atomic. So that means that instead of happening in this order, what if T2 seeded the bucket with step 1 data before the Smurf running for over on the left read its data? Then we would see something like this. Notice that the lines, as far as the lines going down from the T1 box and both of the Smurf boxes and the T2 box, they're still doing exactly the same thing they were doing before. But now the tests over on the left don't see the right data because Smurf on the left read the wrong data. This is exactly what causes this kind of failure. We expected the step 2 data, but we got the step 1 data. So the problem here is what I kind of alluded to before, where we have one bucket for test. Well, clearly that's not enough. If we have multiple test runs running at the same time, what we need is different buckets. That way we won't have different runs of the tests stepping on each other. This turned out to be kind of complicated to do, but once we had it all set up, this ended up fixing the problem completely. Story number 2, out of the void. As a payments processing company, we deal with transactions. You know, that moment where a customer shows up on a merchant's website or in person or something like that, and says, "Here, have some money." And the merchant says, "Hurrah, here, have some goods or services." The life cycle of a transaction can be, well, kind of summed up like this. This is obviously very oversimplified, probably slightly wrong, but we'll just walk through sort of how a transaction moves from being the glimmer in the hopes and dreams of a merchant and a customer to being money that has actually moved from one bank account to another. So we'll start out with a transaction in the pending state. Then we actually check to make sure that the credit card is valid. So that's the authorizing step. Once that's happened, then the transaction is in the authorized state. That's usually when your credit card is approved, or when the transaction is approved, when your credit card is accepted. Then we do, at some regular cadence, a thing where we move all of those transactions into the settling and then settled states. That is basically the step where the money moves from one bank account to the other. As far as your credit card statement is concerned, that's when a transaction will move from the pending section up into the posted section, or down, depending on how your statement is laid out. So let's drill in on that settlement process. This is kind of what it does. In a batch process, because we don't want to iterate over each transaction, there are just enough transactions that would be stressful. So in a batch process, we load up all of our transactions that meet some criteria, and then we say, "Are you authed?" And the transaction says, "Yep." And then the settler says, "Okay, let's start settling you now." Which usually means mark as settled or mark as settling and then do the next thing. This is not the only way a transaction could go, though. If after a transaction is authorized, but before it's settled, a customer comes in and wants to cancel it for whatever reason, or maybe the merchant wants to cancel it for whatever reason, then we void it instead, and then the transaction moves into the voided state. So the way the sequence diagram for that looks is this, where a customer comes in, says void, the transaction says, "Okay, I'm void now, you can move forward." And then the settler comes in and says, "Hey, transaction, are you authed?" The settler says, or the transaction says, "No, actually, I've been voided. Please don't settle me." And the settler says, "Okay, I'll move on to other things." Here's the bug. Occasionally, every so often, very rarely, but more often than zero, a transaction that was voided got settled. This was obviously confusing for any customer who saw it. "I voided you. Why did you settle?" So what happened? Well, if the settler asked the transaction, "Are you authed?" and then after getting confirmation that a transaction was authed, then the customer comes in to void it, at that point, the settler doesn't know any better. So the settler tries to settle it anyway. In other words, from both the perspective of the customer who voided the transaction and the settler, they're still doing the right thing. The customer thinks that their transaction has been voided successfully, but the settler thinks that this transaction should be settled. This is a thorny problem to fix. The fundamental thing here that we need to make sure of is that we're not ever transitioning between the settling and voided states. That's easy enough to do in one direction because when you try to void a transaction, that happens in the context of a web request. So we can always block that. We can always check the transaction and say, "You're settling? Okay, then you can't be voided." But going the other way is a lot trickier because it's in a batch job. And because it's in a batch job, that means that things can happen after we load it. We don't want to lock the whole transactions table. That will freeze the system. That's a bad idea. And we don't want to check each transaction right before putting it into the settling state, because that will end up incurring a lot of requests against the database. So what we ended up doing, and I just think this is so diabolically clever, what we ended up doing was throw a timeout in there. So what the settler does now is, instead of immediately settling the transaction, it marks the transaction as you're about to become settled. So then in this use case, the customer comes in, tries to void the transaction. The settler tries to mark the transaction as I'm going to try and settle you, which the transaction accepts happily. But then when the settler comes back and says, have you been voided? Or basically, should I still settle you? The transaction says, yes, I've been voided. And no, you should not settle me. The reason the 60-second timeout here is so important is because any web request has to complete within 60 seconds, just part of the HTTP standard. So as long as this happens within a 60-second timeout, any void requests that were initiated before after we started the settlement process before we started the settlement process are guaranteed to have completed. So what happens if a void request happens in the other order, if we marked the transaction as settling before the void request came in? Well, at this point, then the transaction knows that it's about to be settled, and so says, no, I'm sorry, you can't void me. You'll have to find another remedy for this. And then the customer, maybe they're not the happiest because the transaction they wanted to void, now they can't void, but at least they don't think that it voided when it didn't. So now we've gone through two fairly different stories for handling race conditions. And the impact they have are very different. The place where the type of defect that they caused was very different. And the remedy was very different. So remember that the secret sauce of a race condition is multiple processes interacting with data with the same shared data, expecting things to happen in a certain order, and then having them happen in a different order. So the first remedy, which is what we used in Smurfs Law, is separating the datas. Basically, have multiple processes, but have them use different data. That just makes the problem go away entirely because now we don't have the shared data anymore. The remedy we used in Out of the Void is rigging the race. Basically, we said, we want things to happen in a certain order, and we can actually guarantee that they will. So we do have a couple of other types of ways that we can remedy race conditions. And in order to deep dive into those, well, we have two more stories. Story number 3, Ghost the In Machine. Yes, that is not a typo. Although, considering the handwritten nature of these slides, there are no typos. Anyway, Ghost the In Machine. I mentioned that in a previous life, I worked on an Internet of Things platform. This is kind of how that works. You have a thing and you have an internet. And the thing sends data to the internet for the internet to process. In this case, we're sending two types of messages, a sensor data, in this case, temperature reading, and a heartbeat that just says, I'm online. You can continue marking me as online. So here's how the internet thinks about the things. We keep track of the sensor data and the status and the last time you were updated. And the timestamp's important because the internet is a terrible place and you might end up with data that's stale or something. So if you get stale data, like in this example where the temperature reading that came in is actually older than the data that we had before, then we don't want to update. Like, sure, you were 65 degrees at that point, but still the most recent reading I have for you is 60. All right, here's the bug. The bug was, for some devices, we noticed that their sensor data was just never getting updated. As soon as you turned it on, you'd get one reading that got reflected in the server. But after that, nothing. We just saw that value freeze. So what happened? Well, it comes from kind of a subtle way that particular device was sending heartbeat and sensor datas. Specifically, it was sending them as separate messages. And we had one device that had a sensor that was really delayed. So heartbeats would often get sent at the right time, but then sensor data messages would get sent delayed by enough that they were pretty much always already stale by the time the server received them. So in this case, even if that 81 degrees was up to date at time 30 seconds, because the heartbeat came in and updated the timestamp to 40 seconds, the sensor data got dropped as stale. Okay, this one's thorny because the server's data model, the fundamental problem here is that the server's data model was just not built to handle heartbeats and sensor data coming in separately. And it certainly wasn't built to handle messages reliably coming in the wrong order. So the right remedy here, remember we've talked about some remedies already, the sort of right remedy here is to restructure how the server thinks about its data model, to change things so that it actually handles those messages in a way that makes sense for the devices. I'm going to call that do handle good, with sort of all the hand waviness that implies, because that's hard and it differs wildly from project to project. There is another solution, and it's the one that we ended up going with. We noticed that this problem was impacting our test devices. We had one device with a very slow sensor, and the way that we were set up in our test environment caused that to impact everything. Nobody else had this problem, which meant that this never happened in production. So the other solution, which we ended up doing, is won't fix. This is a perfectly reasonable approach, by the way. Restructuring your entire data model incurs a lot of risk. It incurs a lot of engineering time, which could be spent doing other things. And when the bug is not actually impacting anything in production, not fixing it is sometimes the right call. Story number 4, Screaming Zombies. We had a tool called postoff. This is at Braintree. We had our Ruby code that sent some data over to a Java process that then sent that data formatted in a certain way to one of our partners. This turned out to be very challenging. Sending data to a partner is always fraught with difficulty because, additional web requests, partner might have an outage, we just might experience some random latency on our own. And this particular task, the data didn't just need to be sent to the partner, it needed to be sent pretty much 100% reliably and very quickly. It was basically useless if this data was sent with a delay of more than 5 minutes. So for all of this to work, we needed monitoring. So what we did was we needed monitoring of the sort what is the latency of this request? How many requests are successful? How many times have we tried to interact with this partner? Things like that. So the way that we had our monitoring set up is we used a metrics provider, and we sent data to that metrics provider using a thing called statsd. So the way statsd works is you write the value of some variable to statsd, and you can do that whenever you want, and then statsd will, at some regular intervals, usually every 10 seconds or something like that, write the data to the metrics provider. The thing that's happening here is that I really want to jump up and down on is that value of foo equals 6 never gets sent to the metrics provider. That's because before statsd bundles it up to send to the metrics provider, we've already written the value foo equals 7 and overwritten 6. So the way that we did this in our code was we instantiated an object of type reporter. Here we have a nice happy reporter. We instantiate it, we call start on it, and then we write our data to that whenever we feel like. And then the reporter at its cadence, which doesn't have to match statsd's cadence, writes foo equals 5 to statsd. The code that accomplishes this is devilishly simple. We have a method that we define in order to work within the framework that's running our code called start, and another method called stop. Start sets all this up and has the metrics reporter start sending its stuff, and stop doesn't do anything because everything gets garbage collected when we get stopped anyway. All right, here's the bug. We noticed that our data was disappearing. We would see actual useful values and metrics up until some point, and then it would drop to 0. This was weird, especially because we couldn't figure out what type of thing could cause this. We also noticed that when in worlds where this was being run on different machines, it would drop to 0 one machine at a time. So the graph didn't always show us that something had dropped to 0. Sometimes it would just fall a little bit if we were not looking at things by machine. All right, so what's happening? Well, remember when I said that everything would get garbage collected? Yeah, that wasn't true. So here's an example of what actually happened when stop and start were called on our code. Stop was called, didn't do anything. Start was called, which created a new reporter and started that new reporter. So then we would start writing data to that. But the old reporter is still there. So if you look at the top, it starts out as a nice happy reporter. As soon as we forget about it, it becomes a zombie process, a zombie thread. So we have the real reporter saying foo equals 6, and then a zombie reporter saying that foo equals 5. This seems bad enough, but stop and start aren't just called every so often. The framework that we were working with here would call them all the time, which means that we didn't just have one zombie reporter reporting some data that was a little stale. We had hundreds of them running at the same time, each writing foo equals 0. Now with statsd only bundling that data up every so often, that meant most of the time statsd would be reading 0 and sending that to the metrics provider. So we ended up with real data that a real reporter is trying to say, getting utterly drowned out by other zombies screaming empty nothingness, not into the void, but into our otherwise very useful graphs. This turned out to be one of the hardest of these problems to debug, but it was the easiest to fix, because the way to deal with zombies is to get rid of them. So, remember when I said stop didn't do anything? Well, the fix was this extremely complicated one-line change to make the metrics reporter stop reporting its metrics. Remember how we had a number of different remedies for race conditions? We had separate datas, rig the race, various ways of saying if we have multiple processes trying to interact with a shared source of data, don't do that, or allow them to count on things happening in a certain order. Well, the one other thing we can do is get rid of processes. When you don't have more than one process interacting with the data, then you don't need to worry about race conditions anymore. And the fact that the processes that we created were created by accident doesn't really change that fact. I hope that you've enjoyed following along and going on this journey with me through some of the race condition woes that I've experienced and that I've heard about from my colleagues at different times. I wanted to share a lot of these stories with you, partly because they're fun. I learned a lot and was very entertained by experiencing and by learning about the various things that can go wrong here. And also because race conditions can happen anywhere, especially in the distributed world that we're living in now, where most apps are deployed with redundancy, with your code running on this machine and this machine, sharing a database, things like that. These are things that need to be top of mind basically all the time. in order to make sure that your systems are continuing to work robustly. And finally, I posed a very important question at the beginning of this talk, which is, what is the sound of a zombie screaming? And the answer